All right, this is the last chapter for our geometry class. Basically, we're just going to drop everything and move over to circles. There are going to be some triangles that pop up in the circles, but for the most part, this entire chapter is all about circles. So the objectives for this chapter are to identify tangents, secants, and chords, use properties of tangents to solve problems. Okay, this video might be a little lengthy because of all the new words. Again, here's all the words that we're going to learn. If you want to write them down now, go ahead. If not, wait till they're in the video. First word is interior of a circle. This is not a buzzword. It's just the first vocab word we're going over. The interior of a circle is the set of all points inside the circle. The exterior of a circle is the set of all points outside the circle. This should be a pretty simple concept for us to grasp because if I draw this, the black area is the interior. The outside area over here is the exterior. I thought this was going to show a blank open circle, but it doesn't. So anyway, a circle has an interior and an exterior. So the interior, here's all the exterior. I think that's pretty simple enough for us to start grasping. All right, go ahead and draw this diagram down with all of these words. A chord is a segment whose endpoints lie on a circle. So notice how a chord stops on a circle. A secant, which is your first buzzword, is a line that intersects a circle at 2 points. So chord and secant are very similar, except a secant keeps going. A tangent is a line in the same plane as a circle that intersects at exactly 1 point. So right here, a tangent basically is a line on the circle that just barely touches it at only 1 point, where secant uses 2. Tangent's basically just like a line that starts going, and then it barely touches the circle. That one didn't. Let's try that again. It just barely touches it right there. Pretend it touched. And then it's done. It doesn't touch the circle anymore. The point of tangency is just where that tangent line touches the circle. So the circle and tangent line are going to intersect, and where they intersect, that's the point of tangency. All right, so identify each line or segment that intersects circle L. When we draw circle, the symbol for it is going to be circle with the point in the middle. Because if I just drew this, you're not going to know if it's an O, a 0, a circle. So a circle, we're always going to put the point in it. All right, so let's name all the chords. A chord is a line that lies on the circle at 2 points but doesn't go through it. So K to L, or K to M, sorry. K to M is the chord. Okay, there's also another chord. It might be hard to see right now. So if I look at this circle, a chord is a line that only touches on 2 points. So JM is kind of like a chord, but it's also a secant. So when I write JM like this, it's a chord. Might not have enough room. When I write JM like this, it's a secant. So make sure you're able to distinguish the two. Secants always have a chord. If I just use the points, it's a chord. If I put the arrows above it, then it's a secant. KM, you cannot put arrows because it doesn't continue on. All right, the tangent, here's the tangent line. This M is the label for this line. There's no other point. You can't just say line H. So we're going to say the secant is M. The diameter, this was not on your diagram, but I believe from middle school, algebra, whatever, we're all pretty familiar with what a diameter is. Diameter is the one that goes from all the way through the circle at the center, all the way through. So Km is our diameter. Notice Km was also our chord. So a lot of these lines may be multiple things. All right, now we want the radii. Radii is the plural form of radius. And basically all we're going to do is I want to look at how many lines start at the center and stop on the circle. So I see 1, 2, 3. So we have 3 radius. We have KL, we have JL and LM. Okay, so notice how we have those three different ones. Any point that starts at the center and ends on the circle is a radius. All right, here's another diagram. We've got congruent circles. Two circles are congruent if and only if they have congruent radii. So if the radius of this is 2 and the radius of this is 2, they're congruent circles. If the radius of this was 1 and the radius of this was 3, they are not congruent. So same radius. The radius is what depends on how big the circle is. All right, then we got concentric circles. Concentric circles are coplanar, which just means they lie on the same plane, on the same paper, with the same center. So these are concentric circles. One will always fit inside the other, or they may be the same circle and they lie right on top of each other. So concentric circles are just inside circles. All right, your second buzzword is tangent circles. Two coplanar circles that intersect at exactly one point are called tangent circles. So notice how there's two different types of tangents. There's internally tangent, where the circles are concentric and tangent. So they kind of are following this rule and this rule. Notice this red dot is the center for the red circle, and the blue dot is the center for the blue circle. Up here, the black circle, the black dot was the radius for both. So anyway, internally tangent. Notice how they share that little point right there. That's why they are tangent circles. Now here we have externally tangent. Still the same idea. They touch at one point, so they're tangent circles. Basically, if the circles lie inside each other, then they're internally tangent, and if they don't, then they're not. All right, so they want us to find the radius, find the length of each radius, identify the point of tangency, and write the equation of the tangent line. So let's start at R. This is all in a coordinate plane, which is nice because I have all these points that I can plot. First, I want to see what my grid is in terms of. Sometimes they'll change the grid and put it in units of 2. Sometimes they'll just leave it as 1 unit apiece. Sometimes it may be 10, 5, whoever knows. So I want to check to make sure I know what my units are written in. To get from the center, I go 1, 2, 3, 4, so I know this is just a simple graph. But if this were to say 8 out here, then I know each little jump is 2. 2, 4, 6, 8. But since it only took me 4 steps to get there, this is just in a units of 4. Most of the time they'll just be straightforward. Sometimes if it's a story problem, it may be the graph may be in hundreds or tens. All right, so let's check out the radius of R. The radius, the length of it is just going to be how many jumps do I need to get from the center to a circle, to the edge of the circle. So I'm going to go this way. I go 1, 2. So the radius of circle R, this is supposed to say circle. Radius of circle R is 2. Now I need to go to S. Start here at the center. I go over 1. And I don't necessarily go all the way over another one. I only go over about halfway. So this is 1 jump and a half jump. So the radius is 1.5. All right, the point of tangency. The point of tangency is going to be where these circles touch each other. And right here is where the point of tangency. I need to figure out what unit or what grid point that is. So starting at 0 to get to here, I go over 2, so I go -2 in the x direction, and I stop. I don't go up or down, so I didn't go anything in y, so it is 0 for the y direction. So the point of tangency is at -2, whoops. Point of tangency is at -2, 0. All right, now the equation of the tangent line. So I need to find, here's the point of tangency. And I've got this line a tangent line going straight through them. I need to figure out what the equation of this red dotted line is. Well, since I know it's a horizontal line, my equation is going to be some type of y equals something. Horizontal lines, when I graph them, are in terms of y. It's opposite from what you would think with the axis. The y-axis goes up and down, but when you graph a line, it goes left to right. Horizontal. So y equals what? How many do I go up and down from the 0 line? Well, I don't go any. So y is just equals 0. That's the equation of this line. All right. Next thing is a common tangent. A common tangent is a line that is tangent to two circles. This is your third buzzword. Notice how I've got two different circles going on here, A and B. L is tangent to this at A and at B at this point. M is tangent to this circle at here and here. Since they are both tangent to two different circles, lines M and L are common external tangents. Key word here, make sure you write down external, please, with this diagram, because the next diagram you're going to see is an internal tangent. It's going to be pretty cool. So this is an external tangent. They're on the outsides. They don't cross or anything like that. They're on the, here's kind of the inside area of the two circles, and this is on the outside of it. All right, so like I was saying, this is still another common tangent, same word, same definition, except this one, this example is an internal tangent. Please write internal, bold it, highlight it, whatever you need to do. Notice how they are inside. They cross each other. So if they cross each other, they're internal. They cross on the inside. And if they don't cross each other, they're external. All right, so here's our first theorem of the chapter. If a line is tangent, please write this down. Diagram, if you want to do the table, perfect. If not, don't worry about it. Just make sure you know what's going on. If a line is tangent to a circle, then it is perpendicular to the radius drawn to the point of tangency. So basically what they're saying is that if this point is tangent, if this line is tangent, I can draw a radius to the point and it's going to be a right angle. Down here, it's just saying the same thing but backwards. If the radius and line of tangency forms a right angle, then M is tangent to C, the circle C. Again, same thing. So tangent lines, the key thing going on here is the right angle, perpendicular. We're going to have right angles going on wherever a tangent line is there. So tangents form right angles. Tangents form right angles. If I said it 3 times, it might be pretty important. All right, last theorem is this one. If two segments are tangent to a circle from the same external point, then the segments are congruent. So what this is saying is I've got 2 tangent lines going on here. There's this one and there's this one. They're both tangent at 2 different points, but because they're both tangent at the outside point, AB and AC, they're going to be congruent. So again, congruent just tells me that I can use equal sign when I set things equal to each other. All right, this is our last example. HK and HG are tangent to circle F. Find HG. So key word here is they're tangent to circle F. And since they have the same outside point, GH is going to be equal to KH. And that's really the only thing that this problem is saying. And they want you to find the distance, find HG. They want you to find this length right here. So what I'm going to do is I'm simply just going to put in GH is 4 plus 2a, so I just put in 4 plus 2a on the left side. KH is 5a minus 32. And I solve. Subtract the 2a over. I get 4 equals 3a minus 32. Add the 32 to both sides. I get 36 equals 3a. Divide out the 3. And I get this becomes 12 equals a. So that's cool and all, but that's not what they want. They want HG. So since HG I know to be 4 plus 2A, now that I know what A is, I just substitute it in. So I have 4 plus 2 times 12 becomes 4 plus 24. So HG is 28. Now that's all they wanted. They only wanted what HG was. They didn't ask what HK was. But to make sure you did it correctly, you could plug this back in to HK, and because they're tangent, they should be the same length. So let's do that just to check our work. So I'm going to plug 5A minus 32. I'm going to plug the 12 in. 5 times 12 is 60. Let's do a little 60 minus 32. And I get 28. So again, I should get 28. It's not a coincidence. I set them equal to each other. I got 12 to be A, so 28 and 28. But the answer is HG equals 28.